Okay, well, thank you for the invitation. Before I forget, it's absolutely standard to forget to mention your collaborators, but I won't. This is joint work with Chuck Doran and Matt Kerr and Pierre Vanhove. I'm an algebraic geometer. First of all, I've been asked to give a talk that's not too technical, that is accessible to a general math audience, and so I'll try to do that. And if at some point I fail, please stop me before we get too X-rated. The content of this talk is something that's very simple, really. Algebraic geometry at its roots studies algebraic varieties. And the simpler the algebraic variety, the more accessible the study is. And classically, one studied, for example, hypersurfaces. And for hypersurfaces, sort of the golden point is degree 3. And roughly speaking, hypersurfaces of degree 1 or 2 are too easy, and hypersurfaces of degree 4 and more are too hard. And so you're like the little girl choosing between the bowls of porridge. 3 is really just right. And I was completely, well, so there's an interesting, so we want to study hypersurfaces, or certain hypersurfaces of degree 3. So that means, if you're not used to thinking about such things, we'll have some x defined by some f equals 0, and f will be f of some x1 up to xn, and f will be homogeneous of degree 3, right? So x then will sit as a closed hypersurface in projective n-1 space, where this projective space has homogeneous coordinates x1 up to xn. Okay. So I should mention classically, I guess the high point was the work of Clemens and Griffiths studying. I won't go into detail, but they had a very, very beautiful study of smooth, by and large smooth. So maybe I should say that, of course, immediately the classification breaks up into 2 parts. We could consider the case when x is smooth, which means that the partial derivatives of f have no common zeros, or the contrary is x is singular. And in their work, they focus on the case where x is defined by f of, I guess, x1 up to x5. So that meant it was a hypersurface in P4, and the dimension x was 3. Right? Now, the interesting Pierre Vanhove is a physicist, and he alerted me. Well, actually, I previously talked a lot with Dirk Kreimer, so maybe I should add Dirk Kreimer. He's not collaborating in this particular project, but certainly I've been very much influenced by his ideas over the years. And in particular, he has a paper on this particular subject called the two-loop master integral. It's an old paper, but it really was my start in this direction. So what are we talking about here? Well, let's make believe that we're physicists. I should say, for a mathematician to talk about physics is a little bit funny, right? I compare it. My grandson, his name is Aiden. He's now 10, but about 5 or 6 years ago, he was very interested in trains. And so we bought him a model train for Christmas. And on Christmas Day, we sort of opened it, and it was kind of a disaster because it immediately became clear that nobody in the household was going to be able to put this train together. Right? And so we had visions of this little kid being completely miserable for the whole day. But actually not at all. What happened was that even though the train was clearly impossible, the box had these fantastic pictures of trains on it in full color and really very exciting. And he happily spent the whole day looking at the box. Right? Now, that very much resembles the situation with mathematicians in physics. I mean, physics is too complicated. It's too precise. It has its own rules and so on. There's really not much chance that a mathematician is going to penetrate the world of a working. It's not impossible. Really smart mathematicians have done it, but it's hopeless for me. But on the other hand, the box is fantastic. You know, you have all these kind of problems that are at root mathematical problems. And so here's one of them. In perturbative quantum field theory, the game is you want to approximate something, I don't know what it's called, amplitude or something. And you do this by writing down a collection of graphs, or more precisely, of Feynman diagrams. Feynman. There's an N, right? I think there's an N. Feynman diagrams. So what are Feynman diagrams? Well, as a first approximation, they're graphs. So I'll draw sort of a stupid graph here. And the edges are labeled by masses. So we have mi here on each edge. We have a mass. And at the vertices, we have momenta. So here we have momenta pi, but pi is not a scalar. It's a vector. So it lies in a vector space of some dimension d. And with this object, to this object, you associate an amplitude, which is, so if we call the graph gamma. So A of gamma and the M and the P, which is the amplitude. And then you sum this over all the Feynman diagrams in your theory to get the answer. Okay? Now, to calculate this amplitude is really a problem in algebraic geometry. This amplitude is a period. And let me tell you a small lie. It's a period which occurs in a certain geometric setup. And so what is the geometric setup? Well, there is a polynomial, which is called the second semantic polynomial associated to this graph and to the various kinematic parameters, the masses and the momenta. So it will depend on the masses and the momenta. And the degree, it will be a homogeneous polynomial. And the variables, the set of variables is the set of edges. So we have polynomial in edge variables. So in this case, they're 1, 2, 3, 4, 5. And it will have degree equal to the number of loops plus 1. So in this case, there's one loop, so this fellow would be a polynomial degree 2. Okay? And so now let me say something that maybe is slightly technical, but I can't think of a better way of saying it, so I'll just mention it. We have this x. If we have, let's say, suppose we have n edges, then this x sits inside projective n minus 1 space. There's one less. The projective index is one less because you have the homogeneity, which drops. So n variables cut out a space of dimension n minus 1, or are variables on a space of dimension n minus 1. And so those of you who know about cohomology, or we can look at h n minus 1, and this I just mean sort of Betty cohomology, nothing too elaborate, of p n minus 1 minus x relative to, I'll write capital delta, and this simply means the union of coordinate faces. Okay, so well, let's see. Can I do this one, for example? No, I'm up in too many dimensions here. In any case, so this is an open manifold, and then relative to a closed submanifold. And we're going to consider this thing, we're going to take this thing when x is defined by this f, which is the second dimension. Okay. So obviously you want to start out with the simplest case. So, well, actually, the simplest case would be if the graph had no loops at all. That's not a totally trivial case, but let me leave that aside because it doesn't involve really any periods. It's sort of a totally rational calculation. So let's start with the case when there's one loop. And then it's the physicist, it's a physics theorem by, get the references here. The physics theorem by, yes. The paper that I know is by Davidovich, D-A-V-Y-D-Y-C-H-E-V, right? And Del Borgo. U-R-G-O. And what this the paper is, well, the title is not very interesting. I think that you can probably find the paper just from the names of the author. But roughly speaking, what the paper says is that for one loop, the period is a dilogarithm. So maybe I didn't say it quite clearly. The period in this case would be obtained by integrating. So that is, you integrate a chain in the homology of this configuration, P n minus 1 minus x relative to the coordinate faces, against an algebraic, a suitable, not any, but a suitable, or a certain algebraic differential form and this yields, on the one hand, this yields the amplitude, but on the other hand, the theorem says that this, so this yields yielding amplitude. But the study of the particular integral that these physicists did shows that it is expressible as a dilogarithm of some complicated expression involving the masses and the momenta. Okay, a dilogarithm is essentially the integral of log 1 minus t dt over t. I'll put that in quotes because, of course, it's not quite so simple as that. There are various changes of coordinates and various manipulations. But essentially, that is the nature of the period that one gets. So this is the one-loop case. Okay, well, obviously, by induction, we would like to next consider two loops. And there, things kind of stalled. I hope I'm not insulting somebody in the audience, but I have the impression that there was incremental progress in looking at particular two-loop graphs. I'll draw some pictures in a minute. But overall, one didn't have any real overall picture of what the story was. So I want to propose such a picture. I can prove 4 or 5 examples. And these examples are of sufficient generality that they're pretty convincing. That I know at least, or that we know, myself and my collaborators, know at least half the story. Half the story means that we have to consider only the case, or for purposes of this talk, I considered only the case when the graph has an odd number of edges. So let me talk about the case. I'll add the condition that we'll talk about an odd number of edges. Okay, so let's draw the nice thing about two-loop graphs is that it's pretty clear what they're going to look like. Okay, that's called the sunset or the sunrise, depending on whether you're pessimistic or optimistic. It has two loops, right, there and there, and it has 3 edges. I mean, of course, you can do other things. I mean, you can look at something like that, but this is not physically interesting. Physically interesting would be to take such a thing and then to put in some little hairs. Okay, where you imagine that you have momenta coming into the graph at these various places, and as well as here and here. Okay, so what can we say about two loops? And I want an odd number of edges. Let's see if I did it right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, well, okay. Now we have an odd number of edges. Well, so let's look at the story. First of all, we'll take the simplest one with no subdivisions, right? These are points, so they're vertices here, so the lines get divided, the edges get divided. So in this case, there's just one momentum. And overall conservation of momentum says that basically it's flowing through. So whatever comes in here has to go out over here. Right? So in this case, the second semantic, so let's call these things, name the edges x1, x2, and x3. And the second semantic looks like this. So f is something like m1 squared x1 plus m2 squared x2 plus m3 squared x3 times x1 x2 plus x1 x3 plus x2 x3 minus x1 x2 x3. And this is the so-called massive second semantic. And I should have said that earlier. I want to include masses. I mean, many times physicists study the case when there are no masses. Masses are all 0. But I want masses. And in fact, I want, for my purposes, I want to study the generic situation. So I'll take all m's and p's to be general. Of course, immediately physicists will say, oh, no, but we're interested in a case where something special happens. But as a mathematician, it's hard for me to anticipate. So it's better first to look at the general case. So sorry, you're absolutely right. P squared. Right. So now we come to sort of the theme of the talk. You say, well, if you know a little bit about algebraic geometry, you know that this f here, so it's a degree 3, so-called x, defined by f equals 0. It's a degree 3 curve in P2. And you'll certainly believe if I tell you that for general values of the masses and of P, notice P squared, I maybe didn't say, P was a vector, but it's a vector in a vector space with a given quadratic form, so-called Minkowski form. And so P squared means P dot P. So this is a scalar. Right? So it's a degree 3 curve in P2, and in fact, it's an elliptic curve. That means for a degree 3 curve to be an elliptic curve, it simply means it's non-singular for general values of these things. OK, well, that's really not a big surprise, because in fact, any degree 3 curve which is non-singular is an elliptic curve. So the fact that we get an elliptic curve is not so surprising. However, what happens is, now let's look at a more general case. So I have a list of examples here. The theme of this lecture is that for degree, or for 2 loop graphs with odd number of edges, elliptic curves are everywhere. And in particular, they play an absolutely central role in this, let's call this a motive. That's what it is. And so I want to explain that it's to some extent a conjecture. I mean, what's going on is that we have maybe 5 different examples, and in each case, and they get more and more surprising, in each case out pops an elliptic curve. So maybe I'll explain by looking at the most, well, let me just draw some pictures here. So here are some examples. First of all, there's this one, which you see is gotten by subdividing into 3 the bottom edge of that. So then the next one is the so-called kite, which is this one. And then the next one I hope I have some time to say something about is what's called the, so this is I don't know what to call this one. This one is the kite. This one is the so-called double box. These are all prominent graphs in the physics world. And then there are the more generally the double n-gons. Notice if I have a double n-gon, let's say, 1, 2, 3, 4, 5. It has an odd number of edges, is the point, because this is symmetric with that, but there's just one common face. And so these fit into the rubric of 2 loops and an odd number of edges. And if we look at the picture here, this, so we have hn minus 1 of p n minus 1 minus x relative to delta. Well, if we want to analyze this motive, the delta is sort of secondary. So let me simplify my life by first looking just at that. So that's sort of an approximation to the geometry that we want ultimately to get. And we know that this maps to n minus 2 in homology of x with some twist, which don't worry about. Basically, the problem is that x can have singularities. In fact, x always will have singularities. So the usual Giesen sequence doesn't quite work, but there's a variant where we take here homology. And so if we want to understand the place where this period, this dilogarithm would appear, we need to understand, in the first instance, we need to understand this guy. And he is dual, I ignore the twist, he is dual to the cohomology, hn minus 2 of x dual with some other twist. So we need to understand this hn minus 2x. Well, it's still kind of hard, but there is the most interesting part. So we want to understand the interesting part. And the interesting part for a hypersurface is always the middle dimensional cohomology. Not always. No, that's not true because of singularities. But the first place to look here for interesting behavior is the middle dimension. And that is to say, is hn minus 2. Understand hn minus 2 of x. And what do I mean by understand? Well, this can be complicated But what one can imagine is that one takes some resolution of singularities. So it's a singular manifold. We somehow resolve the singularities, and we get a y which is smooth. And then the cohomology will pull back. So if I call this map pi, I have a map pi upper star from the middle dimensional cohomology of x, so h n minus 2 of x. X is a complex manifold, so to have complex dimension n minus 2 means that n minus 2 dimensional cohomology is the middle. The top cohomology is 2n minus 4. So this is the middle, and it pulls back to h n minus 2 of y. And now, on the one hand, we will have captured the most interesting nugget of information if we can understand this h n minus 2 of y. And what I'm telling you is that in these three cases, and I'll tell you a bit later, to some extent in this case, we understand. And in these cases, what this is h1 of some elliptic curve, depending upon the various masses and momenta. So E depends on m and momenta, with some twist that I won't get into. But basically, elliptic curves dominate the geometry of, at least in the situation with odd numbers of edges. And for those of you familiar with Hodge structures, I mean, what we can say is that the the highest weight piece of this of this cohomology is a twist of h1 of some elliptic curve. So this is an elliptic curve. Okay. So what does that suggest about the physics question? What can we say about these amplitudes, these periods? Well, what it suggests, and I stress this is a conjecture, it's not, I mean, it's first of all very vague, and second of all totally conjectural, that we would expect that the period, the amplitude, for two loops in the odd number of edges, so odd number of edges, we might expect that these should be elliptic dilogarithms. Well, I don't want to claim I can prove that. I haven't tried yet, actually, but it seems plausible. So what I want to do is give you some sense of, first of all, how amazing this is. In the double box case, just to get a sense of how amazing this is, in the double box case, which is the most complicated one that I've investigated in full detail. So the double box, so just by way of example, maybe I'll put it over here, get a little more room. So by way of example, the double box, it has 1, 2, 3, 4, 5, 6, 7 edges. So it's a hypersurface. So X is a hypersurface in P6. So it's a cubic. This is a cubic fivefold. And we are interested in h5 of x, or more precisely in h5 of a desingularization of x, if x were smooth, then h5 of x would have dimension 42. And in fact, it would be the h1 of an abelian variety where this has dimension 21, and always with some twist, if you know about Hodge structures. In the smooth case, this would have weight 5, and this has weight 1, so you'd have to have, I suppose it would have to be a -2 twist to get the weights right. But so what's happened is that a 21-dimensional abelian variety has somehow collapsed to a 1-dimensional abelian variety. So maybe another example, if we look at the kite, what happens is that x, the hypersurface, so now we have 1, 2, 3, 4, 5 edges. So it's in P4. So x is in P4. So it's a cubic, x is a cubic threefold. But as we'll see in a minute, x has 4 double points. And by, it's not automatic, but it's natural to expect, and in fact, in this case, it happens, that each of the double points, I should have said that if x were smooth, so if x were smooth, we would have that h, the middle dimension, so it's a 3-dimensional thing, so h3 of x would be h1 of an abelian variety, I guess now twisted by -1 to get up to weight 3. And this abelian variety would have dimension 5. Right? So therefore, this would be, in fact, a 10-dimensional vector space. It has dimension 5, but what happens is that each one of these double points drops the dimension by 1. So the 4 double points mean that A gets carried over to an E, which is an elliptic curve. Okay. The other example, the house. Maybe let me leave the other example aside for a few minutes and just try to give you a little picture of what, from an algebraic point of view, what this x looks like. So I need to put it up here. So let me just talk some algebra here. So let's consider a picture like this, and we'll subdivide here. And so here we'll assume that up here we have p edges, and then we'll subdivide here, and we'll assume here we have q edges, and we'll subdivide here, and down here we have r edges. And so p plus q plus r should be odd. Right? And that's the situation. So we have the xi, which are the edge variables. So it's natural we start out x1, xp plus 1, xp xp plus q, xp plus q plus r. Okay? So I want to describe to you a cubic polynomial f in x1 xp plus q plus r. And the way it works is like this. So remember, I'm taking general masses and momenta. So I'm not too concerned about the particular values, just so long as they are general. So what you do is you write down q of x1 up to xp. And this is to be degree 2. So this is to be a quadric. And again, I want it to be general. So some general linear combination of degree 2 monomials in these variables, times, I just add up the rest. So here I have xp plus 1 plus xp plus q plus r. So a quadric times a linear, that's degree 3. And then I do the same thing again for the middle. I take a different, I'll call it q prime, a different quadric, this time in xp plus 1 up to xp plus q. And then I'll multiply that by, again, by the remaining variables. So I have x1 plus xp plus xp plus q plus 1 plus xp plus q plus r. And then I do it again. And you can kind of imagine the story. I have here xp plus q plus 1 up to xp plus q plus r, and then times the x1 plus xp plus q. And that's not quite enough. And so now I have a term that is simply linear in each of the 3 sets of, so I've sort of subdivided my set of variables into 3. I mean, I have the 1 to p, and then the p plus 1 to p plus q, and then the rest. So I have now a sum over general, sort of let's call it a, I, j, k of xi, xj, xk, where 1 less equal to I less equal to p, and p plus 1, p plus 1 less equal to j less equal to q, p plus q, and then the rest, k, p plus q plus 1 less equal to k less equal to p plus q plus r. Okay? And that description is a sort of very simple algebraic description, is really a powerful tool in understanding the geometry of the situation. So first of all, I glibly said that we take our x, defined by f equals 0, and we take a resolution of singularities, y. So this is a resolution of singularities. Well, that's usually kind of easier said than done. Right? And we're going to actually have to control it very, very precisely, because we want to make statements about the most difficult cohomology group, the middle dimensional cohomology of y. So fortunately, with this description and with general coefficients, we can say a very precise thing. Namely, the singular, first of all, the singular locus, x sing, is a disjoint union of 3 quadrics. So let me call them, say, Q1, well, Qi, I equals 1 to 3. And Qi, so Q1, for example, is defined by, I'll set all these variables equal 0. So I'll say x p plus 1 equals equals xp plus q plus r equals 0. And that gets me a linear space. But inside that linear space, so that linear space, I've killed all the variables from p plus 1 onward. So I'm left with the variables from 1 to p. And so I also, it makes sense to look at q of x1 up to xp. Okay? And I do the same thing here. I define another quadratic q2 and another quadratic q3 involving these variables and these variables. And you easily see that I get a disjoint union of 3 quadrics. And with a little bit more work, you find that those quadrics are exactly the singular locus of x. And with still more work, and here I have to be careful, I haven't checked in full generality, but I've checked the examples, that if I blow up, so I take y, I blow up, well, I take v, let's say, to be the blow up of q1 disjoint union q2 disjoint union q3 in the projective space, so that's Pn minus 1. So V is a very simple object. It's obtained by blowing up these very simple quadrics in projective space. And then I take my y to be equal to what's called the strict transform of x in V. So I have a picture like this. Let me get the eraser and draw a picture. Oh, actually, this eraser is cool. Right? This one's kind of glued on. So just by way of example, let's look at the kite. So in this case, let's see, P is 2. So here there are 2 edges up here, so P equals 2. Q is 1, and R is again 2. So we could say this is a 2, 1, 2 graph. Right? So what does F look like? Well, P was 2, so I have a quadric in 2 variables. So F looks like this. F is Q of x1, x2 times the rest. X3 plus x4 plus x5 plus, and now here's a tricky point that I didn't perhaps emphasize originally. This q prime is going to be on the edges between p plus 1 and p plus q. But there's only one such edge. So here, the q prime is just a quadric in 1 variable. But it's general, so I have to put in a coefficient, so let's call it an a, times, and what is a quadric in 1 variable? It's just the square. So here I have x3, I guess. So a is a general. And then this gets multiplied by the edges, so x1 plus x2 plus x4 plus x5. And then I get q double prime, which are for the bottom edges. So 1, 2, 3, 4, that's x4 and x5. And then I have the remaining edges, x1 plus x2 plus x3. Okay? So where are we? We said that the singularities occur on the intersection of the zero locus for the quadric with the remaining variables. Okay? So the effect of killing the remaining variables is simply to leave us just with the variables inside the quadric. So we have here a quadric in two, homogeneous of degree 2 in two variables. So the zeros, the common zeros, so q of x1, x2 equals 0 equals x3 equals x4 equals x5, this is just 2 points. Right? I mean, this is a quadric on the projective line. It has 2 zeros. Right? So I get 2 points. And then here also I get 2 points. That's a total of 4 points, 4 singular points. Here I don't get anything because x3 doesn't vanish. This is on P0. P0 is a point, and x3 doesn't vanish at that point. Right? So there's nothing here. So I get a total of 4 singular points. And that's well, I mean, you have to analyze what sort of singular points these are. But those are, I told you, there were 4 in the case of the kite. There were 4 double points. And so here we have 4 double points. Okay. Well, I should say a little bit more. Let's go. I had hoped to talk a little bit about this fellow, but time is maybe a little tight, and I hate to get rushed at the end. So let's talk about the general case a little bit and give you a feeling for how you do this kind of calculation. So how to calculate the cohomology of y. So the geometry is then this. I'm taking a general case. I have a v, which is here's Pn minus 1, and this is obtained by blowing up some disjoint quadrics. Okay, so this is a very nice, very simple space. Inside here I have my hypersurface x, which is singular, and inside here we have the strict transform, which is this y, which you have to check. It's a little tedious, but I've done it at least in the cases I claim, that this is smooth. And so what we need to do is to calculate the cohomology of y. Well, to do that, given the simple nature of v, it's more or less equivalent to calculate the cohomology of v minus y. Right? And here, I think it's due to Doran, maybe Dimka, Doran, and Dimka. They have a way of calculating the cohomology of open varieties using differential forms with poles. So differential forms on v with poles on y. And let's see, I wrote one down here. Where did I write it down? Yeah. Right. So let's do the case, the one that I wrote down, and I'm going to get confused if I don't follow my notes. So let me do one of the ones with 6 edges. Sorry, 1, 2, 3, with 5 edges, right? So we'll do one which I will not be specified. So this will be either this guy, or the kite, this guy. The key point being that there are 5 edges. Okay, and we want to calculate. So what do we want to calculate? We want to understand, in this case, y is a threefold. And we want to understand h3 of y. But now here we will use Hodge structures. What we want to show is that, so this has, with no twist, I'll skip the twist, this has weight 3. So we want to understand f2 h3 of y. So this is, remember, the Hodge structure looks like this. We have f0, which is everything. So this contains f1, which contains f2, which contains f3, which contains 0. Okay. Now, what I want to show is that f2, h3 of y is isomorphic to C. Okay. That will actually, you have to show a little more. You have to show that f3 is 0, but let's focus on this. So how can we do this? Well, what Deligne tells us, and Deligne and Dimke tell us, is if I look at h4 of v minus y, then we're going to want to understand f3 of h4, because this will map via a Giesen map to f2 of h3. And because v is so simple, this map will actually be an isomorphism. So we want to understand this. And they tell us that I can understand this by looking at the following thing. I'll look at omega 3 of v with simple poles on y. So this means differential 3 forms on v, differential 4 forms, 3 forms, right, on v with a simple pole on y. And if I take the derivative, if I take the exterior derivative of such a 3 form, I'm going to get a 4 form on v, but it can have a double pole on y. And what we need to compute, since we want to compute something in h4, is we want to compute the hypercohomology in degree 1 of this complex. Okay, well now I'm more or less out of time, but let me just say the general procedure. How can we do this? The point is we want to throw this back to differential forms. So we want somehow to turn this complex into a complex of differential forms on the projective space, on P4. So remember, V sits over P4. And this map was pi. And what we do by a careful analysis tells us that we can ignore, in fact, for the particular forms that enter into our calculation, it will be the case that the higher Ri pi lower star of omega j with a twist, with a non-trivial twist, so star, which is not a 0 twist, is 0 for I greater than or equal to 1. So there's no higher cohomology for these differential forms with poles. And the effect of that is that the forms that we look at down here are, I call them omega tilde P4 with poles on now not on y, but rather on the original x. And omega tilde P4 for poles on 2x, and so forth. And so I have to just tell you what these omega tildes are. Omega tilde p4, let's say n times x, is a certain subsheaf, let's say omega j, is a certain subsheaf of omega j p4 n times x with no tilde. And these are the differential forms whose pullback, so pi upper star of omega, so differential forms of omega, whose pullback up to v has no pole, or have no pole on the exceptional divisor. So remember, we got v by blowing up these quadrics. So we had p4, and then we had v, and this was had some blowups. So that means inside v we have we blew up I forget maybe E1 and E2, maybe two quadrics. And these are the exceptional divisors. And so what we have to understand is the subsheaf of forms downstairs with poles on x of some order, but with the property that when I pull them back to v, they have poles, of course, on y, but they don't have any poles on the exceptional divisors. So I'm out of time. Let me stop there. But I hope I at least gave you a sense that this is a very doable problem. And we will know within some finite period of time whether it's reasonable to conjecture that all the amplitudes for two loops involve elliptic dilogarithms. Or possibly, my fondest hope that I wasn't going to mention is that for the even edge case, that in fact everything is mixed Tate, so it's somehow simpler. But that's just a wild guess. I don't know that. But I'm pretty convinced, and I don't have time, but I was going to show you a little bit more about this calculation, how the non-trivial elements come up, and how delicate it is, that I'm pretty convinced that we're going to find that for two loops, everything is either an elliptic dilogarithm or simpler. And that would really be a nice result for a physicist, I think. So I stop there.
Any comments, questions?
Yeah. So in fact, in the middle dimension, it's equal, with a up to a twist. So the middle dimension is two-dimensional, and it is the cohomology of an elliptic curve with some twist depending on the Tate. I mean, if you keep track of Hodge structures. Why is this blow up? Now, it's not x. X is singular. Why is this desingularization of x? So what happens is by going to the desingularization, you lose all the junk. You just are left with the one piece which is going to be important. The rest is going to yield Tate things. But this guy is interesting. Well, the degree is 3. I mean, these are all cubics. So x has degree 3. Y, we can't talk about degree because y is a divisor in V, and V is not a projective space. Y is more complicated. But fortunately, we can calculate the cohomology of Y in terms of differential forms on the projective space with certain properties. And that's the story. So, I don't have a motivic reason, but I have a physical reason. And the physical reason is that I was told after several drinks by an unnamed physicist that physics was special, and that the mathematics that came out of correctly posed physical problems was always the most special case possible. And so what's the most special possible case? In elliptic curves. Now, that is not a terribly convincing argument. But, you know, it's the best I can do. And I mean, this is mathematics. I check these things. These things are true. So, we'll see.